Hey guys, we're going to be doing another video, and this time we want to come at you guys with a harder question just to see if we can do it and also if you guys can follow along. This is definitely one of the hardest ones that I've done. And let's kind of break it down so you don't have to spend all the hours that we spent working through this. So, okay. The question is longest increasing path in a matrix. And what we're basically doing here is that we're given a matrix, which is a 2D array. So it's an array with arrays nested inside of it, as you can see right here. And it basically visually it's going to be formatted the way it is over here. So 994.668.211. And what they want us to be doing here is to find the longest path that exists where the numbers are going to be increasing as the path continues. So in this situation, they showed us that if you started at 1, the next number would be 2, and you could go up to 6, and then the 6 would go up to 8 or 9. However, in those cases, you were only going to be going through 3 different numbers, whereas over here you go to 2, you go to 6, 9, that comes back as 4, and so the longest path is going to be the 4, whereas the other paths going from the 1 to the 6, 9 or 1, 6, 8 would be 3. So therefore, the answer that they want is actually the length of that path. So that kind of saves a lot of work on our end because we don't need to keep track of the path. And that's one like huge thing that we don't need to worry about. So again, for this, you would look through all of these numbers and you would have to find the one that has the longest path. So this 3 going on to the 4, which is larger than 3, then the 5, larger than 4, 6, larger than 5. And this would be again 4. And that is going to be the largest path in this matrix. And then they give one extra case, which is really just an array with a subarray inside of it, which is just one number. And so that they want us to return back as 1. All right, so working through that logic, what we're going to see visually is going to be this. I wrote out the first test case, and they want us to basically do a search through this whole matrix. And there's 2 different ways that you can go about this. So number 1, we know right off the bat, we're going to be traversing through the matrix. And we also know that we're going to have to do either a depth first search or a breadth first search. So I'll write those out over here, depth first or breadth first. And what these searches are basically, they're going to be done very differently. And depth first is basically when you go in and you look at a certain number and you're going to be evaluating each path, or you evaluate one path at a time is basically what it means. So this one is going to be one path at a time. So right now, if you started at the 9, you can't really go anywhere because the 9 over here is not larger than this number, and the 6 is not larger, and it doesn't have any neighbors to the other sides. So one other thing that I didn't explicitly mention is that we are going to be considering the neighbors to be the 4 different directions as listed right here, left, right, up, or down. So we're not going to be going diagonally, just 4 directions. So what we want to be doing is thinking like, okay, we're going to traverse through this matrix. And starting at this path, we don't really have any neighbors that we can go towards. Then we look at the next number and it's going to be a same story. Basically, there is no path because there is no number that is larger than that number, which would be the 9 over here. Then we go to the next number, and 4 does have neighbors that are going to be larger. So one path that could be taken is over here, the 9, or it can go down to the 8. So if it goes to the 9, we already know that you can't go anywhere else. If it goes to the 8, you can see that we don't really have any other direction that it can go either. So we know that if we started going backtracking a little bit, so if we start at the 9, our longest path would be 1. The longest path on this 9 would be 1. The longest path on this 4 would be 2, going either way. So it doesn't matter which way you take. Again, they don't want us to return the longest path. They want us to return the length of the longest path. So this case would be 2 here. Then we go on to the next number, the 6. 6 can't go this direction, can't go this direction, but it can go up here. So this would again be a path of 2 if we only look at that 6 over there. Then this 6 over here, just working through the same logic. Again, you can go up or right. Then it would be 2 either way. Looking at this 8, we already know we can't go anywhere. Looking at this 2 over here, you can go up. And as we already discussed, you can go up again. And that would be a total path length starting at this 2, it would be 3, right? And then you go on to the next one, and this 1 can go over to the 2. And we know that if you started at the 2, the path length from that 2 is 3. And if you include the 1 as well, then it would just be the 3 plus the 1, and that would give you 4. So even though the pattern is kind of hard to see, what's basically happening here is that we're traversing through the matrix and we're looking at every single number, every single option that we have that can be connected together, creating a path following the conditions that we have set in this question, which is that the next number must be larger. We can see that if we started at this, it can go up. And so from 6 to the 9 would be 2, the path length. And then if we go from this 2, it would be 2 going to the 6, which would be a path length of 1 plus this 2 that we already know. Then we can look at this 1 over here. And if we connected that into this path, we already know that over here, right, at this position, the path length is 3. So then the 1 going to the 2, and then adding up all the other paths that already exist in the 2, the largest one at least, which is the 3, it would be 3 plus the 1, the number itself, right? So that would be 4, and that is the number that we're trying to find. So the pattern here involves a larger concept called memoization. And what that basically means is that we're going to be traversing through this matrix, and we want to be using, number one, depth first search, right? Because we want to trace that path all the way through before we start working through another path. And so that is, of course, the biggest difference between these two concepts, depth first and breadth first. If we did a breadth first and say we started at this 6, we would follow this 6 over to the 9. 6 would evaluate this number, then this number, then this number. And there you wouldn't really see much of a difference between depth or breadth. But the difference would come if you start evaluating a number like a 2 down here. It would evaluate the 2 and then work up that way. And then it would look at the 1, ignoring the fact that the 6 could go forward. It wouldn't evaluate that right away. It would come back to it after. So depth first, summarizing all of it, depth first is traversing the entire path before going on to a different path or checking any other paths. Whereas breadth first is going to be checking every other number closest to it as it checks each path. So breadth first is going to be ideal in some situations, but in this case, for this question, since we are looking for the length of the longest path, and we're going to be doing that through depth first. So what that involves is basically working with a stack. And this can be done in two different ways, right? So if we are working with a stack, we can do it iteratively, or we can do it recursively. And really the preference goes to, I guess, whatever you want to do, but usually people go for recursion, and that's what we're going to be doing. It's a lot easier to write the code for, actually, I don't know if it's easier, but it is less code when it comes to recursion, and it is going to save on some of your space complexity. So you're going to have better space complexity working through recursion versus doing iterative. And we did kind of do it iterative. It was having some issues in terms of timing when it came to some of the final tests. So we had to kind of swap over to recursion anyway. So that's how I recommend you guys handle this question. And yeah, we're going to get more into the depth as to how to solve this next. Okay, so before we start up on the actual coding and how to solve through this problem, there's a few concepts that do need to be explained just a little bit. I won't go into too much depth because they are huge topics, but yeah, so as we said, right here, we are going to be using depth first, and depth first uses a stack, whereas the difference between breadth is going to be using a queue. So the way that a stack would be working is the last item in is going to be the first out. So again, trying not to go into too much depth, but yeah. So what we can do is if we go through the iterative route, what we would basically have to do is set up our own stack, and we would call it, we would consider it a variable inside of our function, and then we would initialize it as an array of arrays or a matrix. But since we're going to be doing recursion, right, we're going to set this to a variable. And since we're doing recursion, what we're going to be doing actually is utilizing the stack mechanic that it already exists inside of the event loop here. So we don't need to set up a separate variable for the stack. We would just be utilizing the stack through recursion. So what does that mean in terms of the code here? Well, we're going to have two functions, right? We're going to have our main function, which is basically going to be for our main function, and this one is going to be traversing through the matrix. And we're going to show you how with the code as soon as we get into it. But just to give you a general idea, so main function traversing through the matrix, second one is going to be our DFS, or our depth first search. And this function is where the recursion magic happens. And this function is going to be recursing on itself. And that's going to help us find that path as we traverse through this matrix over here. All right, so let's start working on that pseudocode now. All right.
All right, so first thing we're going to do in our main function. So Wasik mentioned it a little bit before, but we're going to utilize memoization, right? So the way that we're going to do that here is we want to essentially make a copy of our matrix, same length and width or whatever, like if you think of it as a square or a rectangle. And we're going to at first fill all of those values with something, it's sort of arbitrary, but here we're going to use -1 because eventually we're going to want to compare other values against those values inside of our depth first search function. So what we're
Mm-hmm.
going to end up with is something that looks initially like this. If I can kind of see here, it would look like that basically. And then as we go through, we would change these to the max path length from that index, right?
Mm-hmm.
So if this one was 4, you know, then this one was maybe 3 or something like that. But
Yeah. Yeah.
eventually they will all be at least 1.
Mm-hmm.
Um,
Yeah, so it's a little bit easier to visualize. So let me do a little bit of illustration here. So it's basically what I was going through here. I was trying to kind of show it off. I don't know if that came off, but basically with memoization, what we're doing is optimizing our speed in other words, our time complexity. We want it to go as fast as possible. And so what we're doing is we're running these DFS searches as we traverse through our matrix. And at some point, the DFS is going to be hitting, say, this 4 right here. It's going to look at the neighbors, right? Which is going to be this 9. And we already have the result of 9 stored in our memo. And because of that, we can just grab that result and just add it to what we have right now. So we know that we were discussing before that the 9 can't go anywhere, right? So it can't go left, right, up, down. So we would store this as a value of 1 because the longest path that you can have from that 9 is 1. Then we go on to the 4, and what's going to happen here is that it's going to look again, left, right, up, down, 4 directions, and it's going to say, I can't go over to that 9. And we know that the 9 is a 1, right? Because that's the value, that's the longest path that you can have from the 9. And going from the 4 to the 9 is 1. So the total path length here would be 2, right? So it would be the 1 from here plus the 1 from there, and that would give you 2. Then it's going to do another special thing where it looks all around, right? So it looked at that one, these two don't exist. And then it looks at this number and it can go down. Because it can go down, it's going to do the same thing where it says, okay, it's 1 coming from here because this path is 1 from the 4. It's always going to be 1 if it's the number itself. And then it can go over to the 8, but we don't have a saved we don't have any saved data on that 8. We don't know how far you can go from the 8. So that's where that DFS comes in, and it goes on to the 8 and it says, how much farther can I go? So then it looks at the 8 and it says, what are the neighbors? Can I go anywhere? It's going to say no. And so that value is going to also evaluate to 1. And so we're going to have the same situation here where it's 1 plus 1 giving you 2. And we're going to store the largest number from both sides, right? Or any of these sides onto this number right here in our memo. So we have a separate matrix that is a 2D array, just like this example right here, which we're passing in with the values. And that is only going to be storing the paths that can be taken from that value itself. So here, it's going to be 1. Here, it's going to be 1. Here, it's going to be 2. And here, it's going to evaluate that 1. And what's going to happen then is that you have another memo or a matrix with the cached results being stored looking like this. And so the other values, as Henry was saying, we're just going to put -1s there for now. And so we're going to continue traversing that matrix. Going to hit the 6, and then the 6 is going to, of course, look at the 9 and say, okay, I can go to the 9. I can't go anywhere else. So then this memo is going to be formed as 1 plus 1, same as the other side, right? Same as these, the 4 going to the 8, same as the 4 going to the 9. The 6 going to the 9 would also have a path length of 2. So when we come here, we're going to change this value to 2. And so we start to form this memo, or a stored data structure of our results of the longest paths that we found through our DFS. So we're going to use that to figure out what is the longest path. And that way we don't need to, for example, come over to this 8 again and then run another DFS as soon as we go through the 6, and then come back to the 8. We don't need to run another DFS on that same number that we've already run a DFS in the past from the 4, because we already have that data there. So that's going to save a lot of time. And pretty much, like, this is a requirement for this question. There's no working around that. Trust us, we definitely spent a lot of time trying.
We got what, at like 155 out of
100,
158 or something.
135 out of 138.
That's,
And we
yeah,
had
we
to
were missing 3.
refactor our entire solution because of
Yeah.
that. Insane.
Yeah, we
Anyways, yeah.
basically
Yeah.
we're using memoization to save ourselves from doing depth first search when we don't need to. That's like the long and short of it. It's
Yep.
like it's difficult to understand just talking about it, but when you see the code, it makes sense, because our depth first search function has a conditional in it that says, hey, if this equals -1, then run DFS. Otherwise, just return its value. That way we're saving ourselves from running DFS. And DFS, running it that many times, is going to get really expensive, especially on like a bigger array like this one. This was one of the
That
3
was the
that we
one.
couldn't pass.
That was
Yeah.
the one.
And you know what, it would have eventually run it, but it would have been probably like next
Yeah.
year or something like that,
Yeah.
And I don't think Leetcode allows you to run your solve for a year. So
All right,
yeah,
let's keep going with that pseudocode.
yeah. So okay, basically we want to create, this blank memoization copy, that we will then fill in as we go with memoized values. And then after that, we're going to want to iterate through our matrix. Okay. And in each iteration, we're going to want to compare. Oh, actually, before we iterate, we're going to want to initialize a max value. And we'll probably initialize it to 0. Then we're going to compare what we get from running the DFS to our current max. And if it's bigger, we'll set the max accordingly. Okay. And then finally, when all is said and done, we'll just return our max. Okay. So that's our main function. Okay. Cool. So we're going to come in, we're going to set up our memo copy. And it's just going to be a new array set to the length of the matrix for our outer array. And then we're going to fill it with nothing, basically. And then we're going to map that array. And we're going to map it with more arrays, except this time they're not going to be filled with nothing. Okay. They're going to be filled with a bunch of -1s. Okay. So that is our kind of blank copy. That's what we're going to use to memoize these lengths. And then we're going to set up a max length, start it at 0. And then we're going to do our actual iteration, right? And the way that we've done it is using for each. And what we're really wanting from this is like the row and column indexes. And when you do a for each, you can have like the actual element, and then you can also have a second parameter, which will be that index, right? So that'll be our outer one, and then our inner one will be that L for each on it. Column.
Let's call it like L2.
Yeah. I mean, since we're not using it, it's not super important, but yeah, just to make it make sense, and then we are going to set our max value to equal the maximum between the max and running DFS. And in DFS, we're going to want to send our max value, or not our max value, our matrix, row, our column. We're going to want to send -1 for that first one, and then our memo. And then finally, at the end, we're going to return max.
Okay, so first thing we're going to do, and like we mentioned before up here, first we want to check if that element exists. So you can group this into 2 different base cases, but we kind of just jumbled them into one. But I will explain it so it's easier to follow. So the way that I think about it is that you want 2 cases for your rows, which is going to basically track the index of the row, because you don't want that index to go beyond the length of your actual your matrix, right? So the matrix's length is going to be your limitation for that row, or the upper end of that limitation. So I'm going to say that row should not be less than 0. And of course, the way that we're writing these out basically means that if it is less than 0, then we're going to be going into this base case and stopping recursion, right? So that's why the actual block inside of this conditional is going to be return 0. So keeping that in mind, if we do meet these base cases, we want to stop recursion. So if that row, which is an index, right, is less than 0, we want to stop recursion. So we want to go into this base case. And then the other case is this separated by this operator, which is the OR operator. So if this is true, which is that if the row is greater than the length of the matrix, right? So in this situation right here, we would see that the length of the matrix is 3, right? Because there's 3 rows or 3 arrays inside of it. So the length of this would be 3. So we want it to be less than 3, right? Because we know that the first index is 0, second is 1, third is 2. So we want it to be less than the actual length. If it is more, then we want to stop recursion. And that's why we want to be looking for the cases where it is higher than what it's supposed to be. Then you do the same thing for the columns, right? If the column is less than 0, or if the column is greater than or equal to the matrix. But here, in this case, we want to look at the individual rows, because the columns are going to be these individual arrays, right? So we want to, the columns are going to be these elements inside of it, right? We made these columns to be what they are, and we're counting them as elements inside of this subarray. So we want to look at the first subarray, which is going to be identical in length to every subarray inside of it. So it might not be a square.
You can see that like in the constraints of the problem. Like if you scroll down to the bottom,
true.
Yeah,
right there. So yeah, we know that the length of every row, right, is going to be the same, and we know that the length of the matrix, so we know that the length of each row is going to be, I already that out. It's weird when it does that word wrap. Okay, so matrix at that first row, which is going to be this 3, and the length, we want that to be less. So if it's more, then we want to stop recursion because there is no value there. We don't want it to go through recursion on a value that does not exist. Then the second base case, or in this situation, the fifth case that we're going to include in the same statement, you can include it separately, but we're including it all in one, is going to be checking if that value, right, the current value, if it's larger, so the current value would be matrix at row, column, and remember that we're passing in these parameters of matrix, row, column, previous value, and memo. So also very important to pass through the memo because we want those values being retained and cached. And the only way to do that recursively is to pass in every value that you want to be retained has to be passed in every time. So matrix at row column is our current value. We want this value right now to be larger than the value from before. So we're going to say if it is less than or equal to, then it's not larger, right? So we want to stop recursion. So we set it up that way. These are our base cases, got that out of the way. Now let's get into recursion. And the recursion, we have that memo check that we have to do right here. So we're going to do a check if the memo at this row column that we have right now, does it exist? So the way that Henry told you guys was that we set these values up with -1s inside of here. And so up here, all of these are filled with the -1. So right now, this entire matrix or the memo of this matrix is -1, -1 all the way through. So we want to check if that -1 exists, then it means that we have not performed a DFS on that value. We don't know how far that value can go in terms of how much further the path extends beyond that value. So if it is -1, we have not done the search and we need to do DFS. So then we want to check if it's -1. If it is, then we go inside and we're going to do this. We're going to set up our directions, and there's different ways to do this. Of course, a lot of different ways, 4 different ways that I've tried myself. And it all kind of does the same thing. So I will explain this as soon as I finish typing 1, -1. Okay, so what's happening here is that we are setting up our vectors, and what's going to happen is that we are going to do a recursive step right here, and that step is going to be, wow, kind of like jumping all around. Okay, so that step is going to be a for loop where we're going to be doing, I'll call it V, doesn't really matter what you call it. V is less than 4 because you can only have up to 4 neighbors. And we want it to be less than 4 because, again, indexes start at 0, going up to 3, that's going to be 4 neighbors. And what's going to happen here is that we're going to call this max direction, and we're going to be setting that value to DFS. And this is that recursive step. And it's going to be, we're going to be passing in the same parameters that you see up here, right? So matrix, row, column, previous value, and the memo, of course. And the thing about this is that in order for it to be a recursive step, we have to change these values, right? So we're going to adjust this value based on this vector setup that we have up here. So what does that mean? That means that we're going to do row plus row vector. And row vector in this case, what it's doing is that it's going to start at the first, and it's going to look at this 1, and it's going to say row plus 1, and then column is going to be the same situation. Column plus column vector. And the column vector is going to be, again, both of these are at B, which is what we set up right here. Doesn't matter what you call it. So it's going to be row plus row vector, column plus column vector. And what's happening is that it's going to go through these arrays simultaneously, right? So it's going to say 1 and then 0. So it's going to do row plus 1, column plus 0 in this case. So the column stays the same, essentially. The row goes up by 1. So what does that mean in this array or matrix over here? So let's say you're at 2, and if you did row plus 1, you would go down 1 row, right, to the next row, and then you would do column plus 0, right? So it's the same column, right? These are the columns. So it's going to look at this value right here. So what is that value going to be? That's going to be the down direction. Then it's going to go to the second one, which is -1, 0, which is going to be -1 being the row above, 0 column doesn't change, so that's going to be the up direction. Then the next is 0 and 1. So what happens here? The row doesn't change, the column changes. So it goes over 1, right? +1 would be this one right here. So that's the right direction. And then of course, the last one is going to be -1, which is the left. So what we've done here is set up a loop that loops 4 times. We know that for sure every single time, because up here they've already told us that we're only going in 4 directions, right? And so we set up our loop to go in those 4 directions, and it's going to do that with recursion, right? And so that value is being incremented by 1, because we know that the path that you start at, it has to be at least 1, and we know that down here you see when you just have one subarray with one element inside of it, it has a path of 1. So at least 1, which is going to be the path itself, and then we're going to add whatever length can be, whatever length exists on that other direction. So if it's 1 over here, then it gets added into the 4 like we saw before. So it becomes 2, and that gets saved as this const max direction variable that we have here. And then we're going to be doing a comparison, right? So we want to compare this value to the max that we are going to set up right above here. Let max path equal 0, and max path equals max path. Sorry, max, a lot of maxes in here, but max direction, and that's that max direction that we have here. So what is math.max doing? It's taking in a certain number of values, right? Doesn't matter how many, and it's going to compare those values against each other, and it's going to automatically just dump us the largest, or give us the largest number that exists here. And that's what we're looking for. We're looking for the largest or the longest path. So in this scenario right here, where we hit this 1, it's going to give us the path going here, which is 4, over the path going to either one of these, which is 3. So that's what we want to happen. We want that comparison to happen. We want to find the longest path, which is going to be the largest number. And then we exit out of that loop, and we want to create a memo value at this point, and that is going to be equal to the max path that we found at that point. So now we're caching. This is how we're caching or storing our results inside of this memo, so that we can always come back and get that memo without having to go through all of this. That was the point of setting up this if statement. So we're not going to go into this if unless we have not done a DFS here. And if we do go in, then we do recursion on all of the directions, and we set that max path, and we store it inside of our memo under that row column, and we're going to return this row column. And of course, this return is down here so that if that value does exist, we don't go through this, we just jump straight to giving us the value that we want. And with recursion, what's going to happen is that if that value does exist, like this 4 going on to this 9, it's not going to go into here again. It's going to go straight to this. And so it's going to say the 9 is equal to 1 because it can't go anywhere else. The path is 1 at 9. And it's going to go back up through the stack, and it's going to add the 1, which is the 4 itself. So it's going to be 1 plus 1, and that's going to be 2. So I hope that makes sense. That's the best way that I can describe recursion. It's always hard to visualize until you start to play around with the code and really experiment with it, console log as much as possible. I mean, that's how we all learned. So let's get into this testing. This is kind of a long video, so let's try to kind of wrap this up at the end here. So this is a scary looking matrix, but it will run very quickly, efficiently, with this data being cached every time that we do cache it. Okay, just looking through this, there's a few adjustments that need to be made. The max path should be inside of this matrix. I mean, sorry, this block. The if statement, V should start at 0. And previous value is going to be the current value, right? So it's going to be matrix at row at column.
All right, now let's
All right.
really get these tests. Okay.
Let's go.
All right, cool. We got 4 for the first one. That's what we expected. So let's do 2. We're expecting 4 here again. We get 4. All right, now let's do the big, crazy, scary one. 140.
Nice.
Perfect.
And it
Wow.
literally went as fast as the other ones, pretty much.
Yeah.
I mean, maybe like a little bit slower, but like still coming out pretty fast. Whereas the other way that we did the iterative approach, it was sitting there in like loading for like 2 minutes, and it just never even finished. But yeah, so here it is. I'll just give you guys a quick look of the final code, take out some of the pseudocode that we wrote. And if you can scroll up.
Oh, sorry. Yeah.
Yeah, it's like
here,
going back and forth. Yeah, do it.
I hate live share sometimes. Yeah, I'll take out this pseudocode. I want to give a nice full screen.
All right, let me see. Flex it out. Dang. I don't know if that's even visible, but there it is. That's all of the code. And it's only 2 functions, not too bad. It looks worse than what it is. Once you guys start practicing, you know, type it out, console log stuff, you'll see that there's a lot of like little things that you have to pay attention to, but overall, very doable. And hopefully this helps. Thanks for watching, like and subscribe. We'll keep making some more videos.